Welcome to section 4.4, and what we're going to be looking at this week is what is called the second derivative test. Now last week when we looked at the first derivative test, the first derivative helps us to determine where are the maximum and the minimum. So we may end up with something that looks like this. What the second derivative test allows us to do is to determine when is it concave upward, when is it concave downward, and that's actually the first thing that we have to look at for problem number one. And so this is more or less what problem number one looks like, a very rough sketch of it. But here we go, we are asked to find the local extrema. And so if I look at this point right here, it's not too difficult to realize that has the point -3, 6. And so that would be a relative maximum. And then likewise down here, if we would look at this point, this would be the point 3, -6, and this would be a relative minimum. So we've determined the extrema. But now we need to identify the intervals where the function is either concave up or concave down. Now it's important to realize that concave down is always going to have the general shape of a hill because it's concave downward. In other words, it opens downward like this. The concave up would be, of course, the exact opposite. In other words, it's concave upwards, or it scoops up. So we either cover it with a dome or we scoop it up like this. And so the question now becomes, on this particular graph, when does it stop becoming a dome and when does it start becoming a scoop? And hopefully it's pretty simple that are easy to realize. This is where it converts from being concave downward, or in other words going downward right here, compared to upwards right there. It's right at this point. So when would it be concave up? And when would it be concave down? Well, it's concave down from -infinity all the way up until 0. So concave downward would be from -infinity to 0, and concave up would start at 0 and go on forever, or 0 to infinity. And so this is all problem number one, very roughly, but this is the concept of what is called the second derivative test. The second derivative test allows us to determine where is it concave upward and where is it concave down. And so that's what we're looking at today. Okay, 2 and 3, we are asked to graph the equation, and we need to include the coordinates of any extreme points and inflection points. And I guess before I go any further, what is an inflection point? Well, the inflection point is where does it change from being concave up to concave down, or vice versa, concave down to concave up. That's called an inflection point. And so that's what we need to deal with. So let's look at how to do this with number 2. Y equals 2x cubed minus 3x squared minus 12x. And we are asked to find the extreme points. Well, we know how to find the extreme points. We just take the first derivative. So that would be 6x squared minus 6x minus 12. Now, going back to last week, to find the extreme values, all we need to do is set that equal to 0. So 6x squared minus 6x minus 12, setting that equal to 0. I can divide everything through by 6. So I get x squared minus x minus 2 equals 0. And this factor is relatively simple. Simply, x minus 2 times x plus 1 equals 0. Setting each one of these equal to 0, I get x equals 2 and x equals -1. So, looking at what we did last week, I'm going to put in the points -1 and 2, choose points somewhere in between or not on those particular points. So I'm going to choose -2, 0, and 3 and plug it back into y prime. So if I plug in -2, this would be 6 times 4 is 24. -6 times -2 is a positive, so it's 24 plus 12 is 36 minus 12 is positive. Remember, that's all that's important here. If we plug in 0, this is 0 minus 12, so this is negative. Plugging in 3 would be 6 times 9, or 54. 54 minus 18 is what? 36, and 36 minus 12 is 24. So once again, the important thing is that it's positive. So that means it's increasing from there, or during that time frame, decreasing here and increasing there. Now we need to, and we know that negative 1 would then be a maximum, and at 2 would be a minimum, just because of what it's doing. It's increasing and then it starts decreasing at negative 1. So that's a maximum. Decreasing to increasing means it's minimum. Now the question becomes, what is the inflection point? In other words, when does it become concave up, concave down? Well, that's the second derivative test. And as the name would imply, what we need to do is we need to find the second derivative. So the second derivative equals, what, 12x minus 6, I believe. And it's pretty much the same process. We need to set this equal to 0 and go from there. So 12x minus 6 equaling 0, 12x equals 6, and so x equals 1/2, which means something happens at 1/2. Well, let's look at what happens. I'm going to actually put 1/2 there, just like we have in the first derivative test. And just like we did in the first derivative test, I'm going to pick values on either side of it, say 0 and 1. So let's plug in 0 and plug it in here. Plugging in 0, I get a negative. Plugging in 1, I get a positive, because 12 minus 6 is 6. Now, instead of saying increasing and decreasing, what this means is this is concave down, and this is concave up, because that negative means down, positive means up. So now we've got quite a bit of information. We're actually ready to graph our points now. Now, in order to do or figure out what each of these points are, we need to go back to the original to find what are the corresponding y values. So I'm going to have the point negative 1, and if I plug in negative 1 back into the original, I think I come up with a 0. Negative 2 minus 3 is negative 5, and I don't. This is entirely wrong, or at least my notes are entirely wrong. So let's see. If I plug negative 1 in here, I get negative 2 minus 3 is negative 5, and negative 5 plus 12 is 7. So that's going to be my maximum. My minimum is plugging in 2. Let's see, 2, that would be 16. 16 minus 12 is 4, and 4 minus 48 is negative 44. So this is my max, this is my min. And then going to what we just got done doing, we had an inflection point at 1/2 something. So I'm going to plug in 1/2 here, and so let's see, doing a quick calculation, y of 1/2 would equal 2 times 1/8, which is 1/4. 1/4 minus, okay, 3 times 1/4 is 3/4, minus 12 times 1/2, which is 6. 1/4 minus 3/4 minus 6 is negative 6.5, or negative 13/2. And so now and this is my inflection point, because this is where it goes from being concave downward to concave upward. So now I'm finally ready to put this all into a graph. I have negative 1, 7, 2, negative 44, I believe. Isn't that the values? 2, negative 44. Which is way, way, way down here. So negative 1, 7, 2, negative 44. And then I have an inflection point at 1/2, negative 13/2. So I'm going to label that. And so it's going to come up here, it's concave down this whole way, and then right at this point, it stops being concave down, now it becomes a scoop, coming around like this, and then up like that. So now looking at the graph, we realize this is a relative max, this is a relative min, and we have our inflection point. We don't label it as an inflection point, but we do label it as a point because that's the important point there. So the first derivative test is exactly what we did last week. The second derivative test tells us when does it stop being a hill and become a scoop, or when does it stop being a hill and becomes a valley, when does it stop being a valley and become a hill. You know, it works both ways. But the test is pretty much exactly the same way. You find where does it equal 0 and then try values on either side. And then you just go from there. But understand that each of the points always has to still be put into the original so that you get the final correct answer. Okay, let's look at number 3. 3 is y equals x times the square root of 11 minus x squared. And we need to find the maximum, minimum, and inflection points. So the first thing we have to do is to get this into user-friendly form, which is x times 11 minus x squared raised to the 1/2 power. Now, obviously, this screams product rule, and within the product rule, we have a chain rule that we're going to have to deal with. So it's just a matter of getting down to it. So let's find what y prime is. Using the product rule, let's leave that one alone, take the derivative of this one. So that would be times 1/2. The derivative, this would be 11 minus x squared raised to the negative 1/2. And we have to take it times the derivative of the inside, which is negative 2x. Plus, now take the derivative of this, which is 1, and leave this alone. So this is relatively simple, thankfully. And then we rewrite this and clean this all up. So this would become, let's see, the negative 2 cancels with the 1/2. The x times the x would become negative x. Actually, the x times the negative x would become negative x squared. And this goes in the denominator as the square root of 11 minus x squared. Plus, this remains the square root of 11 minus x squared. Now, in order to do anything, we need to put this all into one big fraction. And so that's not too difficult. Our common denominator is 11 minus x squared, or the square root of it, which means we're going to have negative x squared here, plus, now what I'm going to have to do, I'm going to have to multiply this by the square root of 11 minus x squared, which is very nice. It ends up being that. So finally, we get the square root of 11 minus x squared in the denominator, and this becomes negative 2x squared plus 11. Now, and we need to find the critical points. Well, the critical points are where either the numerator equals 0 or the denominator equals 0. But one thing we do have to be careful with is, since this is a square root, we have a very limited range that we can, or a domain issue that we have to deal with. We know that 11 minus x squared has to be either greater than or equal to 0. That's the first thing. And so, solving this, we get 11 is greater than or equal to x squared, or x would have to be less than or equal to, well, this is a little bit different. We need to consider this just a little bit differently, because we ask ourselves, you know, when is x squared less than 11? Well, that's between negative 11 and positive 11. So we know that the only thing we're concerned with is between negative 11 and 11. And it can actually be equal to that because it can equal 0 per se. So that's where our graph is going to range from, between not negative 11. Let me try again. The square roots of 11. Just about messed up royally there. So we're only dealing with between negative square root of 11 and positive square root of 11. Now we need to deal with where do these equal 0. Okay. Well, we've already found where does the denominator equal 0. So we know something happens at negative 11 or negative square root of 11 and positive square root of 11. But we need to figure out where does this equal 0. So quickly setting it equal to 0. subtract 11 from both sides, and divide both sides by 2, we get x squared equals 11 halves, and therefore x would equal plus or minus the square root of 11 halves, which we can just leave it like that. There's no need to rationalize the denominator. So let's see what happens here. I know something happens at negative root 11, or that's the absolute farthest that we have to worry about, and positive 11. We don't have to worry about anything down here or anything up here. And we also know something happens at the negative square root of 11 halves and positive square root of 11 halves. Well, I know 0 goes here, and let's see, this would be 3 is a value in between there, and negative 3 here. So going back to the y prime right here, I'm going to plug it into this one right here, because this is my final answer for y prime. If I plug in negative 3, this would be negative 18. Negative 18 plus 11 is negative, and then this is positive. So negative over positive is negative. So that means this is decreasing at this point. Plug in 0. This is 0 plus 11, so that's positive. Positive over positive is positive. So it's increasing during that interval. And at 3, negative 2 times 9 is negative 18. Negative 18 plus 11 is negative 7. Negative over positive is negative. So we now know at negative 11 halves, that would be a minimum, the square root of it. And the positive square root of 11 halves would be a maximum, because it's increasing on one side and decreasing on the other. Now let's go ahead and calculate those points before we lose track of what's going on there. And so I get the point negative square root of 11 halves. And let's see, what is that particular value? That would be, oh boy, after you just plug it in, I think, yeah, that becomes 11 halves. And I'm not going to go through that. You can spend the time to do that. And if I plug in the positive square root of 11 halves, we end up with 11 halves again, or actually negative 11 halves there. Okay, so, and does this make sense? It really, wait, I'm sorry. This is negative. I apologize, I should have had here. And this becomes positive. Okay, so because I know this is a minimum, this is a maximum, and the way I had it, it just wasn't coming out right. Now it's time to do the inflection point, which means we have to go, here's the first derivative, and so what we need to do is we need to take the derivative of this, which of course is going to take the second derivative. So let's first off rewrite this into a user-friendly form, and then we'll go from there. Y prime in a user-friendly form would be negative 2x squared plus 11 times 11 minus x squared raised to the negative 1/2. So this is a product rule. We could have used the quotient rule or whatever. I just put it in this, and now I can use the product rule and realize the quotient rule is just a special situation of the product rule. So here we go. Finding the next derivative, or the second derivative, we leave the first one alone, times the derivative of the second. Well, this is going to require a chain rule. So it's going to be times negative 1/2, and then 11 minus x squared times the derivative of the interior, which is negative 2x, plus. okay, take the derivative of this, which is a simple derivative, negative 4x, and leave the second one alone. Now we're going to have quite a bit of cleaning up to do here. So negative 2 times the 1/2, that cancels out. The negatives will cancel out. Let's see. Oh, wait a minute. I can't do that. Major mistake there. But this 2 here can cancel with that 2 easily enough. Boy, remember, all of it goes or none of it goes. So don't do what I just attempted to do. So what this ends up being is x times these two multiplied together. So I'm going to go ahead and multiply those together, which is going to require a FOILing. So I get a positive 2x to the 4th. Let's see, negative 11x squared and a negative 22 would make negative 33x squared plus 121. Plus, and then how does this simplify? Not a whole lot. Actually, I can change this to a minus because of the negative, and this would be 4x over 11 minus x squared, the square root of it. And so we end up with this monstrosity up here. And let's see. So to get a common denominator, it's the square root of 11 minus x squared, and then I'm going to go ahead and multiply this out, and because what's going to happen is I'm going to have to multiply all of that by the square root of 11 minus x squared minus the 4x here. So now what we need to do is we need to set each one of these equal to 0. Well, setting this whole thing equal to 0, hopefully it's not that easy to see. This is a very involved problem. But basically, if we look, there's if we could factor out an x out of absolutely everything, which would leave 2x to the 4th minus 33x squared plus 121 times the square root of 11 minus x squared minus 4. There we've got x, which is actually going to make our lives a whole lot easier, and then 11 minus x squared. Well, where does this equal 0? The only place that this is going to equal 0, and really at this point you might just want to look at a graph of this mess. Put it into your graphing calculator and figure that out. But as it turns out, the only place that that equals 0 is when x equals 0. So I'm not going to take the time to put it into your graphing calculator. You should be very adept at doing that. But realize that once we find this, and this is our inflection point, we have to plug this back into the original. So we plug this in, we get 0 times the square root of 11, which is 0. So our inflection point is at 0, 0. So finally, we are finally ready to graph this mess. We know 0, 0 is our inflection point. And we've already determined that at negative square root of 11 halves, negative 11 halves is right here. And way over here would be the point square root of 11 halves, 11 halves. And we know that we have to stop at negative root 11 and positive root 11. And we do have to find these actual values. It doesn't take too long. Plug negative square root of 11 into the original and you get 0. And plug in positive 11 and you get 0. And this is where we have to stop, because it doesn't make sense to go beyond the square root of 11, because then we would go into the imaginary numbers. So it's just a matter of realize this is the minimum, this is the maximum, and this is where it stops being a valley and starts becoming a hill. So we're just going to draw a nice smooth curve going around like this, and then get something that looks like that. This isn't a very good drawing because it's really hard to see that it stops scooping up and starts pouring out here, but realize this would be sufficient for this particular graph. This does take a lot of quite a bit of work, but it's just part of the game. You have all week, but realize you really need to get down to work. Now, my video is getting a little bit lengthy, so I am going to do one more problem and then start another video. So let's look at example number 4. Example number 4, y equals x minus sine of x, and we are restricted to just really one period between 0 and 2 pi, one trip around the quadrants. And we need to find the extremes, the inflection points, so on and so forth. So to find the extremes, we have to take the derivative. Well, the derivative of this would be 1 minus the cosine of x. That's relatively simple. And we have to figure out where does this equal 0. So 1 minus cosine of x has to equal 0. So that means negative cosine of x equals negative 1, or cosine of x equals 1. Well, the only place that cosine of x equals 1 is, well, it's not the only place, when x equals 0 and when x equals 2 pi, which both of them are in the domain, so we need to include both of those. So we know this will be our extremes, 0 and 2 pi. Well, let's look at the values. We plug in 0 back into the original. We get 0 minus the sine of 0. Well, the sine of 0 is 0, and 0 minus 0 is 0. If we plug in 2 pi, let's see what we get. 2 pi minus the sine of 2 pi. Well, the sine of 2 pi is equivalent to the sine of 0. Sine of 0 is 0. 2 pi minus 0 is 2 pi. So hopefully it's pretty obvious that this would have to be a minimum of some sort, and this would have to be a maximum. Now, as it turns out, those are also the endpoints. That's one thing we would have to actually plug in, but as it turns out, since one's a minimum, one's a maximum, we don't really have to worry about it. We've already determined those endpoints. Now we need to deal with the inflection point. Notice that number 4 is actually quite a bit simpler than either 2 or 3. So y double prime means we need to take the derivative of this. Well, the derivative of 1 is 0, and the derivative of negative cosine of x would be a positive sine of x. And we have to set this equal to 0. Realize I did forget to do something here, and that's to determine which one, make sure that it's a minimum and a maximum. Where is it increasing, decreasing? We'll do this here in just a few seconds. But right now I'm going to set sine of x equal to 0, and the only place that happens, well, the only place says that happens is at sine of x equaling 0 is at 0. And pi, and 2 pi for that matter. And so this is somewhat of a special situation. Let's come back here and verify that this does work. So it's going to be at 0 and at 2 pi. I'm going to plug in the value of 1. And really it's pretty simple. 1 minus the cosine of 1. Cosine of 1 is something positive, but it's less than 1, so 1 minus something that's less than 1 is still positive. So we know that it's increasing, and it's increasing everywhere between 0 and 2 pi. That's the first thing we need to realize. It's increasing everywhere because there's no other extreme points there. But we do have chances of it becoming concave up, concave down. So I'm going to choose the value of 1 and the value of 4. Now I plug in the value of 1, and we've already determined that well, this needs to go into the second derivative. So we plug in 1, sine of 1. Sine of 1 is in the first quadrant. You need to think through that. The sine of 1 is quadrant or is positive, and the sine of 4, which is actually in the second quadrant, the second quadrant, or I'm sorry, the third quadrant, not second. Just got messed up there. Ooh boy, got a slight problem here. Where does the sine of x equal 0? Sine of x does equal 0 at 0, pi, and 2 pi. Yeah, sine. The sine of 1 is positive, and the sine of 4, which happens to be in the third quadrant, realize this is either third or fourth quadrant, but it doesn't matter, sine is negative. So we know this is concave up here and concave down here. And where is the important point? It occurs at pi. Well, we have to go back to the original to figure out what's going on here. The sine of pi, we already know is 0. Pi minus 0 is pi. So this is an inflection point. So finally, this is what we get. We have our minimum at 0, 0. We have our maximum at 2 pi, 2 pi. We know it's increasing continuously, so it never goes up, down, whatever. And at pi, pi, it converts from being concave up to concave down. Now, it's not real easy to see that, yes, this is scooping up and this is pouring out, but you have to make sure that it shows that in some manner. We will continue this. Hopefully we will get, well, actually it'll probably be 2 more videos yet, but I will get those up in a little bit. So see you at the next video.